Hello everyone and welcome to our presentation of our paper AnonyNoise, a method for anonymizing event data with smart noise in order to outsmart ray identification and preserve privacy. In this video we will go over our motivation, our method and the results of our conducted experiments. Also feel free to check out our paper using the QR code on the bottom to get a much more detailed description of our method. Otherwise, let's start with motivating our approach. Since cameras are becoming increasingly cheaper and more energy efficient, the amount of public as well as private surveillance has increased drastically in the past decade. On the one hand, one might argue that this enhances the security against criminal offenses like robbery. On the other hand, however, this poses a substantial threat to our intrinsic human value of privacy, which is legally underlined in Europe, for example, under the General Data Protection Regulation. This dual-use character of visual sensors therefore requires a detailed handling and investigation on the necessity of the identification of humans, which is not given for every application like emotion detection for marketing purposes. Previously, event cameras were thought to be privacy-preserving since their sparse output is difficult to comprehend for humans. However, recent research shows the ray identification, as well as grayscale image reconstruction are indeed easily achievable by deep learning methods, thus allowing a detection of individuals by humans as well as machines. In order to combat this, previous work focused on preventing the image reconstruction by training an anonymization network in order to fool a frozen reconstruction network while still allowing a third network to perform ray identification on the anonymized event data. However, we argue that there are many tasks without a need for any identification. In this case, the right of privacy strongly outweighs the benefit of higher security. The goal of our work is thus to prevent all ray identification by neural networks, and not just a single frozen one. At the same time, we still want to ensure the usability of the event data for beneficial downstream tasks. To achieve this, we train an anonymization network for the event input alongside a target network, which performs the desired downstream task, as well as an ray identification attacker network for adversarial training. Next, we will go over the implementation of our approach in more detail. As the name AnonyNoise already suggests, our method includes Gaussian noise for the anonymization process. This is due to the fact that Gaussian noise is surprisingly effective in preventing ray identification, which can be seen in the figure on the right side. However, this effect can be easily circumvented by using a denoising network. Moreover, the target accuracy, which we want to preserve, suffers significantly with a high standard deviation. For these reasons, we are aiming to create a trainable noise, which is more robust and still allows for an easy downstream task detection. The anonymization network also has to be lightweight and simple to potentially run on mobile devices, which is why we choose a simple 6-layer convolutional neural network. The input to the network is the event frame we want to anonymize alongside some Gaussian noise, with a 0 mean and a standard deviation of 1. The output of the network is a per pixel mean and a per pixel standard deviation. Based on this, we construct the anonymized event frame as a sum of the original events, the per pixel mean and the per pixel standard deviation, multiplied with the input Gaussian noise. With this reparametrization trick, we are able to create trainable noise without the need to propagate a gradient through a stochastic node. Our objective is to maintain a downstream task and to prevent any ray identification, which is why the training of the anonymization based on a single frozen ray identification attacker is insufficient. In such a setting, we couldn't ensure that other network weights of the attacker wouldn't be able to overcome the anonymization. We solve this obstacle by jointly training all of the network in an adversarial pipeline, meaning the target network is trained to perform the desired downstream task based on the anonymized data, while the ray identification attacker is trained to still predict the correct identity, using a cross-entropy and triplet loss. This allows for the flow of a strong training signal to the anonymization network, which has a loss that includes the target loss as well as the negative triplet loss, in order to prevent the ray identification. However, given a trained anonymization network, we have to ask the question if an attacker now could simply retrain a new ray identification network, which would potentially render all our anonymization efforts useless. In order to ensure robustness against such attacks, we add a post-training stage after the pipeline training of our anonymization network. In this post-stage, the weights of the anonymization network are frozen and the ray identification and target network are now retrained based on the anonymized data to fulfill their respective tasks. Let's take a look at the experiments we conducted and their results. Firstly, we compare our method against Gaussian noise, after a ray identification attack occurred. We test both approaches on two datasets. DVS-Gesture is a gesture recognition dataset containing 11 hand gestures for 29 subjects, 6 in the test and 23 in the training split. The SEE dataset includes labels for single-eye emotion recognition for 98 subjects, which we divided into a split of 78 subjects for the training and 20 subjects for the validation. As the data in the table on the right suggests, Gaussian noise can effectively protect personalized information, but also leads to a significant drop in target accuracy, which is undesirable. AnonyNoise, on the other hand, achieves a decrease of almost 60% in ray identification accuracy, even after the ray identification attack, while also a high target accuracy can be preserved. Next, we evaluate the generalization capabilities of our approach based on event ray ID, an event dataset for ray identification from multiple camera perspectives. It includes 78 subjects for training and 20 for validation. However, it does not include other labels for a potential downstream task. We apply the AnonyNoise network trained on DVS-Gesture without any ray training on event ray ID. The results can be seen in the bottom table, which show that a 20% reduction of ray identification accuracy can be achieved even after an ray identification attack. This proves that anonymous noise indeed generalizes well to previously unseen data. Moreover, we ablate different input and output configurations for our anonymization network. The results can be seen in the table on the bottom. Regarding the network's output, the data shows that adding the input event frame is significant to maintain a high target accuracy. Additionally, the inclusion of Gaussian noise allows a reduction in the ray identification accuracy by almost 50%. Also, including the Gaussian noise in the input enables the network to predict the output deterministically, which allows for a further reduction of the ray identification accuracy by overall 60%. In the middle you can see the qualitative results of our anonymization method. For all three datasets on the left you can see the original event frames and next to it, the anonymized data as well as the results of the addition of Gaussian noise. On the right side you can find the outcomes of an image reconstruction attack based on the original and anonymized event data. The visualizations show that our anonymous noise method very effectively prevents the identification by humans as well as any grayscale image reconstruction, even though it was not specifically trained for it. This leads us now to the conclusion and summary of our presentation. In this presentation we propose AnonyNoise, an anonymization method based on Gaussian noise, which prevents ray identification by up to 60% while still allowing the execution of useful downstream tasks. For example, gesture or emotion detection. To achieve this, AnonyNoise is trained in an adversarial manner against a ray identification network, making it robust even against additional ray identification attacks after the training. However, our method is limited to its application on event frames, which opens the door for future investigations into different event representations. Moreover, AnonyNoise is currently still task-dependent, which might be resolved in the future by training for multiple downstream tasks at the same time. Here we summarize the references we used during our presentation. Feel free to pause the video to check them all out. This concludes the presentation of our paper. Thank you for your attention. If you have any questions, please send us an email, and do not forget to have a look at our paper.